In section 1.5, we introduced quantifiers, universal quantifiers like for all, and the existential quantifier, there exists. But we can use those in combinations to build even more complex, even more sort of interesting types of mathematical statements. So, especially when you have more than one variable involved, you often need multiple quantifiers. So, as an example, let's look at the statement, for every real number x and every real number y, x plus y is a real number. Okay, so now we're quantifying over two different variables here, x and y. So symbolically, this would look like, okay, for every real number x, that looks like for all x, and every real number y, for all y. I know there's an and in the middle, but you don't actually have to put an and symbol in between quantifiers. And then we have our open statement, our predicate here, x plus y is a real number. So we could say x plus y is a real number. Or, symbolically, remember, this is essentially saying x plus y is an element of the set of real numbers. Okay, so for every real number x and for every real number y, the sum of x and y is a real number. Is this true? This is actually true, but we're not going to prove it here. It's maybe a little above where we're at this moment to try to prove something like that. But when you add two real numbers together, you do indeed get a real number. All right, now what about this for all statement? So this is a universal statement. For all x, for all y, x squared plus y is equal to 9. So this is asserting that for every real number x, again, they didn't put the x as an element of R, but we assume if they don't specify that we're talking about real numbers. So for every real number x, and for every real number y, we're asserting that x squared plus y squared is going to be equal to 9. This is quite simply false. It is false many, many times over. We can find lots of counterexamples to show that this is a false statement. All we need is a pair of numbers x and y that make this equation, x squared plus y squared equals 9, false. So for our counterexample, consider, let's say, x equals 5 and y equals 7. It doesn't really matter. Just make sure you choose an x and a y such that x squared plus y squared is not equal to 9. Right? X squared plus y squared, in this case, would be 5 squared plus 7 squared. It is 25 plus 49. That's 74. Very much not equal to 9. All right. So what does this mean? This means this has to be false, which means its negation has to be true. So what would it mean to negate a statement like for all x, for all y, x squared plus y squared equals 9? Well, let's just try to use the same reasoning that we already have from the last section. If we wanted to negate this entire statement to get an equivalent statement which is true, well, the first thing we would do is sort of negate this first universal quantifier. So I can sort of start from the outside. I know that the negation of a universal quantifier would be an existential quantifier. So there exists an x, and now we still have to negate the rest of it. For all y, x squared plus y squared equals 9. Okay, so now how do I negate what's inside the parentheses here? Well, again, I've got a negation of a for all statement in here. Now, this is just a single quantifier universal statement, and we've seen already that it's going to change to there exists an x, there exists a y, such that the negation of the predicate holds. So now the last thing we need to do is negate that predicate, that open sentence, and we can do that simply by turning that equal sign into a not equal sign. So we get there exists an x, there exists a y, such that x squared plus y squared is equal to 9. And indeed, this is how we showed that our original statement was false. We proved that there existed an x and a y, such that x squared plus y squared is not equal to 9. Right? 5 and 7, those are our x's and our y's. So all you have to do is find one x and one y, and that will show that your statement, that your original statement is false, and thus the negation is true. Okay. Right? Now, in general, you'd have that a universal statement of the form for all x for all y, p of xy, is going to be equivalent to there exists x, there exists y, such that p of xy. Similarly, using that same reasoning, if you negated a sentence of the form there exists an x, there exists a y, such that p of xy holds, you would have for all x for all y. Whoops, negate that p of xy. There should be negation of p of xy on the inside. You have to negate the quantifiers, so switch for all to exists and vice versa, and then you also have to negate the predicate. So p of xy should become not p of xy. Alright, so now we know what to do if we have two copies of the same quantifier. But what if you had a statement that used both universal and existential quantifiers? So let's look at an example. For every real number x, there exists a real number y such that x plus y equals 0. Let's try to write this symbolically first. So I'm going to break this apart one at a time. We start with for every real number x. Alright, this is a universal statement, so for every x, if you wanted to, you could say for every x in R, but remember it's okay to leave that part out because real numbers are assumed. Alright, our next part would be there exists a real number y. So there exists a y. Again, you could put in R if you wanted to, but you don't have to. I'm going to just leave that part out. So for every real number x, there exists a real number y, such that x plus y equals 0. So we use parentheses to say such that x plus y equals 0. So this is what it looks like symbolically. Now, is this true? Okay, we have to think through how we would prove something like that. Now, I know in general, if I'm trying to prove a for all statement is true, I need to give an argument that says, no matter what x value you choose, I can always make the rest of it true. Right? No matter what x value you choose, I should still be able to make the following part of it true. So to prove that this is true, I need to start by letting x be some arbitrary real number. Because this is a universal statement, I need to show that it's true for every single x value. So let x be an arbitrary real number. We must find a real number y such that the statement x plus y equals 0 is true. Can we do that? Well, sure. To do that, I'm just going to try to rewrite this statement in terms of find a y. So I'm going to try to solve this for y. If I solve it for y, I'd get y is equal to negative x. So if x is some arbitrary real number, look, I found a y value, namely the y value would be equal to negative x. That's going to make this statement x plus y equal to 0 true. So let x be an arbitrary real number. Let y be equal to negative x. Then y is a real number, because if x is a real number, then negating it is also a real number. And x plus y would be equal to x plus negative x, which is equal to 0, which is exactly what we were trying to prove. We're trying to show that that predicate is always going to be true. So for an arbitrary real number, we were able to produce another real number y that made that equation x plus y equal to 0 true. So this entire statement is going to be true. Okay, let's look at another example. On the other hand, consider the sentence, there exists a real number y such that for all real numbers x, x plus y is equal to 0. It's a little bit different here. So symbolically, we have there exists a real number y, there exists a y, such that, we don't need to put a parentheses here, we'll put it at the end, such that for all real numbers x, comma, so parentheses, x plus y is equal to 0. Alright, this looks awfully similar to what we had on the last page. Right, on the last page, our statement was, all that was reversed was the quantifiers. For all x, there exists a y, such that x plus y equals 0. This was last page. So now we've reversed the quantifiers, and we have there exists a y, such that for all x, x plus y is equal to 0. This this true? Well, let's see. How would we prove something that's an existential statement? Right, this is overall existential. We have existential on the outside. There exists a y such that for every possible x, x plus y is equal to 0. And we've seen that to prove an existential statement, we need to find a witness. Right, proving an existential statement requires you to find a witness. So you need to find a single x value. Oh, sorry, it's not a single x, it's a single y value that makes the predicate true, that makes x plus y equals 0 true, no matter what x value is chosen. So think of it as a game. You need to pick the y value, and I'm going to try to find an x value that ruins it. Right? Any y value that you choose, I'm always going to be able to find an x that's going to make this statement false. Right? If you try to pick, say, 0, well, I'm going to pick an x value like 1 that's going to make that equation false. If you try to choose your y value to be 1, I'm going to let my x value also be 1. X plus y won't be equal to 0 then. Right? So this seems to not be true. Right? No longer true. You can't find a single y value that's going to make x plus y equals 0 always true. So let's look at one more example. Consider the sentence, there exists a real number x. All right, let's try diagramming this out here. There exists a real number x such that for all real numbers y, we have x times y is equal to y. All right, this is an exists for all. So this is sort of like example 2 here. All right, now again, to prove that this is true, we would need to find a single witness, a single x value, so that, or such that, x times y is equal to y is always true, no matter what y value is chosen. Can you find such an x? Can you find an x value that's going to make this equation here, x times y equals y, always true for every single possible value of y? You should be able to think of one, right? What can you always multiply y by and get y back again? Well, that's going to be 1. So this is actually true, and here's why. Our witness is going to be let x equal 1. Then essentially what we would need to show is that for all possible y values, we have 1 times y is equal to y. So I've just taken my predicate xy equals y and replaced x with 1. Is this a true universal statement? Is it true for every real number y that 1 times y is equal to y? Yes. This is true, right? No matter what real number you choose, if you multiply it by 1, you get that real number back again. So that means the entire overall existential universal statement is true. So the whole statement is true. Okay, so in general, how do we show that a particular statement is going to be true or false? It depends on what quantifiers you're using, but also the order of those quantifiers. So in the next video, we'll go through and try and walk through every single possible combination of quantifiers and when do you show that they're true versus when you show that they're false.